All right, it's recording. So a student, let me see. You guys see my window, right? So let me see. Yeah, you see it? Thumbs up, something?
Yeah.
Okay. All right, so a student asked today about these homework assignments, and I just wanted to be clear about it. Like, so when we say like assigned homework problem, page 10, the thing about the homework is some of the earlier problems in each of the chapters are kind of integrated into the text. So you'll see them kind of in the chapter text, and then the later ones will be kind of at the end of the chapter. So I just wanted to make that clear. And so this shows the textbook, and like that first problem, I said problem 3, page 10. That means it's page 10, which is page 10 of the book, and it's exercise 1-3, which is right here. And you know, these are all pretty doable problems, and I really do believe that if you're able to do the homework problems, you know, with a little bit of struggle, you'll get an A in the class. And also, I think that if you struggle on certain problems, it's a wonderful thing to ask me about in the office hours, and we can go over those kind of problems. Okay, all right. So that's the first thing I wanted to say. Okay, so let's keep going in the PowerPoint. All right, so we're kind of last thing we talked about was resonance structures. And you know, drawing chemical structures. It's not like we're done with that, but we just got to move forward. We will talk tons more about drawing organic chemicals, and you know, what the little lines mean, and CHs, CH2s, CH3s. At the very end of this chapter, and at the end of the PowerPoint, I have some good practice examples. We'll get to them shortly. Okay. But for now, we're moving on to kind of atomic structure, atomic orbitals, molecular orbitals. And molecular orbitals and molecular orbital theory is really a crazy topic, and we're barely going to touch on it. You need to know just a little bit about like hybridized orbitals, and we'll get through that, okay? So atomic orbital theory is a quantum mechanical description of electrons around a nucleus. We describe electron behavior through wave equations, and the energy and the electrons that are, you know, involved in this are settled down into specific energy states. Okay, so we'll see the energy states in a second. All right, now organic molecules kind of go beyond atomic orbital theory. So this is sort of a basic fundamental theory that you've learned about a little bit in Gen Chem. Moving particles, such as electrons, exhibit a wavelength determined by the de Broglie relationship. And this is funny because you might think of a particle as not something that would have like a wavelength, the way like light has a wavelength. But that's what's kind of weird about quantum mechanics, is there's kind of like a wave-particle duality, okay? And so and you don't have to know this for any exams or quizzes, this kind of theory or these equations. So don't worry about this. I'm reviewing it just for your general knowledge, and you'll learn more about this like if you take PChem or something. But anyway, the wavelength is related to Planck's constant divided by the mass and the velocity of the particle. So it's weird that a particle has wave properties, right? And so this defines the wavelength of the electron, which is strange. We're not used to particles having a wavelength. It's not the kind of world we live in. It's a sort of a different world in, you know, where these electrons are moving around. It's a little hard to visualize. Okay. There's this concept of interference of electron waves. And electron waves contain nodes. We'll show what the node is in a second, which is kind of like where the amplitude of the wave changes sign. I'll show that in a second. Waves can interact with each other and either be constructive or destructive. And that kind of, I always think about that as kind of like bonding and anti-bonding. And like, you know, the wave might reinforce itself or de-enforce itself, okay? And so this kind of shows like a normal wave, how it goes up, down, up, down. The plus minus isn't like charge. It's not like positive charge, negative charge. It's just a sign of the wave, right? The wave goes up, down, up, down. And if you have two waves, they can either positively interact with each other or constructively interact with each other, so that it's kind of like they're on top of each other, and then it kind of reinforces. You might think of this as like a bonding interaction with two electrons. And there's the opposite situation where the waves destroy each other. So they're opposite, they cancel each other out. And that's called destructive interference. So this can be thought of as a way to explain bonding and anti-bonding. Okay, we'll talk about bonding and anti-bonding in a second. All right, so then we get into quantum mechanics, and a little squiggly line means that we're not really covering this very seriously, but we bring it up, and you learn, or you take baby steps at this throughout your chemistry experience. And if you take physical chemistry, you'll learn more about quantum mechanics. So the wave theory of electron motion is called quantum mechanics, and so essentially, the way electrons behave, we can explain their position with wave equations, and we can solve the wave equations, and the solution's represented by this psi character. Now that the solution of these wave equations is a very, very hard calculus problem, and so and we don't really need that for organic chemistry. So you learn a little bit about it, and then you will probably see it again later. And if you square the wave equation, you can get the probability of finding an electron at a given point, which is pretty cool, in terms of atomic structure. All right. So without really going into much more detail, that's the basis of quantum mechanics.
What would a wave equation look like?
I'd have to look it up in my PChem book. I don't have it this second, but it's a couple pretty complicated physics terms. Yeah. If you Google Schrodinger's equation, you'll see it, but it's not, for organic chemistry, we don't really care about that specifically. All right, so each wave function corresponds to a specific discrete energy, and the system is said to be quantized, so that we have different specific energy levels, all right? Okay. So the big takeaway is that atomic orbitals have characteristic shapes. This is probably what you know from Gen Chem. Knowing where the electrons are gives us the geometry of the atom, and really not necessarily the atom, but the that's probably a typo, but like the bonding configuration around an atom, where the bonds form. This tells us the possible shape of molecules. Okay. So most importantly, quantum mechanics provides a surface which indicates the probability of finding the electrons at a given time and location. The simplest example is s orbital, which you probably know from Gen Chem, right? It's spherical. So this is like an s orbital, and it's a spherical thing. It's pretty easy to understand and visualize, right? The next high, and that's actually called the 1s orbital, and then we also have the 2s orbital, which is the next higher energy level. Next higher energy level is the 2s, which is also spherical, and there's also for these orbitals, there's kind of this node position, which is like the electrons are kind of in the negative phase or the positive phase, but not really hanging around in the node phase. So the node is kind of like where things don't really exist. That's the easiest way to think about it. Okay. Slightly higher than 2s, we have the 3 degenerate 2p orbitals. What does degenerate mean here? It means the same energy level. So there's going to be 3 2p orbitals that all have the same energy level. And these are shaped like a dumbbell, and they point along the 3 Cartesian axes. So we have the 2px and the 2py and the 2pz. So that's pretty easy to see, right? Little dumbbells. Okay. Okay, and for the most part, organic chemistry deals with lower s and p orbitals, so it makes it kind of easy in terms of this sort of basic theory. We don't really deal with d orbitals or like the higher orbitals in organic chemistry.
I have a question.
Yeah.
Right. So in those models, what are the positive and negative signs indicating?
So again, it's kind of that it's sort of the phase of the wave. The big thing is the middle point is a place where electrons are not existing, and it's a little hard to see without more detailed quantum mechanics. It has nothing to do with sign or like positivity or negativity. It's more of a quantum mechanical wave thing, I guess. All right. So then we have a couple of these principles. You've learned these in Gen Chem. How to assign electrons to the orbitals. And there's a couple principles. One is the Aufbau principle, which is that lower energy orbitals are filled before higher energy. That makes sense, right? Fill the lower energy before the high energy. And so we'll see this in a second. The other one is that this is called the Pauli exclusion principle. No orbital can be occupied by more than 2 electrons. You got 2 electrons total per orbital. Degenerate orbitals must receive a single electron of the same spin before receiving a pair of electrons. That's called Hund's rule. So it's the Aufbau principle, Pauli exclusion principle, and Hund's rule. These are kind of Gen Chem things. You don't really have to know these for this class even. We're not going to really test you on this or anything, but let's just see an example of it as we slowly move forward to using this in organic molecules, all right? So this is carbon in its neutral state, which has 4 electrons, right, in the valence shell. The 1s orbitals are occupied by 2 electrons, and then we have the 2s orbitals. The valence electrons, there's 4 of them. So 2 go into the 2s, 2 go into the 2px and 2py, and then you have 2pz vacant, right? An Aufbau principle says lower energy filled in first, can't fill in more than 2 electrons, and degenerate orbitals must receive a single electron before receiving a pair of electrons. That's what's going on in the top ones. It's not like we put 2 electrons in one orbital. So these are just sort of basic principles and how to fill these orbitals up, okay? Let's think about nitrogen, oxygen, and fluorine, which have 5, 6, or 7 valence electrons. Same exact thing. So this is nitrogen, 5 electrons, fill in the 2s, and then 2p, x, y, and z, get 1 electron. Oxygen, it's got 6 electrons, 2 in the 2s, then you have 2 and just pick one of the p orbitals, and then you have 2 unpaired ones in the other orbitals. So these are the neutral forms of oxygen or nitrogen, or fluorine, which has 7 electrons. 1, 2, 3, 4, 5, 6, 7. So you just fill up the orbitals. Pretty straightforward. And this is really still Gen Chem, okay? Okay, molecular orbitals and covalent bonding. So now we're moving slowly into what's happening with organic molecules. Atomic orbitals on 2 different atoms may overlap, and that'll form a bond. And there's actually kind of like, if you have two atomic orbitals, it'll lead to 2 molecular orbitals. One that's called a bonding orbital, which, what does that mean? It means that it's consistent with a bonding interaction between 2 atoms, right? What do you think anti-bonding means? It means that it is not consistent with bonding, right? If you have an anti-bonding orbital, you put some electrons in there, what happens to the bond? It breaks, the bond breaks, right? All right, H2, simple molecule, very, very simple, the simplest molecule, right? So we have 2 1s orbitals, that's all it's got, and it can form either a bonding orbital, so there's a couple ways you can draw the bonding orbital, or they can, if the signs of the wave functions are opposite, this is where we talk about the plus and minus, if they're opposite, then it forms an anti-bonding orbital, okay? So you actually form both. We'll see it in a second. You form a bonding orbital and you find and you form an anti-bonding orbital. The bonding one is a nice bond. The anti-bonding one, if electrons are moved in there, it will break the bond, right? Here's another way to show it. Through an energy level diagram of the 2 overlapping orbitals. Okay, so let's think about H2 and this theoretical molecule helium-2, which I'll give you a hint, does not exist, cannot exist. H2, though, we know is a good molecule, right? Okay, so H2, you have the 2 hydrogen atomic orbitals, and they overlap to form either a bonding orbital and an anti-bonding orbital, right? The bonding is low energy, the anti-bonding is high energy. Where do the electrons reside, the 2 electrons? They reside in the bonding orbital. So this is actually a stable molecule. We know of hydrogen. I can purchase a tank of hydrogen on, I'll probably have it on the internet, but from a chemical supply company, I can actually purchase it. And we know of hydrogen as a stable gas. It's, you know, it's flammable, but it exists as a discrete molecule, and you can isolate it, right? What about helium-2? Because how many electrons? So we know hydrogen has 1 electron around it. Helium has 2 electrons, right? If you look on the periodic table. So how would helium look? Helium-2. Helium-2 would have 2 electrons in one atom, 2 electrons in the other, and then 4 electrons total, right? And then 2 go into the bonding, 2 go into the antibonding. And is this a happy molecule? Yes or no? I wish you have a thumbs up, thumbs down, but we know. You have a thumbs down? No, it's not. It's, yeah, exactly. You can't. Helium-2 does not exist, and it's because there's no electron configuration that would allow it to. There's no way you could have 2 helium molecules, helium atoms bound, because they occupy the antibonding orbital. Okay, so H2 is a nice happy molecule. Helium-2 is not a happy molecule. Okay, hybrid orbitals and hybridization. This is getting really into organic chemistry, hybrid orbitals. What do you think hybrid means here? It's combining, well, it's like turning a hybrid between like an s orbital and a p orbital, right? And this concept of hybridization. So we're gonna see this like crazy all through organic chemistry. And then really structures. We're getting back into, you know, drawing structures, and then we're moving on to chapter 2. Okay. Orbital hybridization allows us to explain more complex bonding arrangements that are typically observed in organic chemistry, right? sp3 is going to be the shape of a tetrahedral carbon, and you guys know, you should know a little bit about hybridized orbitals and sp3. So a simple example is like methane or something. You have the 2s and the 3,2p orbitals get combined or hybridized to make 4 sp3 orbitals. So we imagine the 2s and the 3,2p's coming together and forming these hybrid orbitals, these 4 sp3 orbitals. And then, you know, like in the example of methane, then 3 H's which just have the 1s orbitals, they and a single electron, they can bind. And what do we now have? We have methane, right? So the carbon is hybridized with sp3 orbital. And you have the 4 H's, and they're bound also. So that's a pretty simple example, right? Okay. So what about sp2? sp2. Here, it's like we have a 1 2s orbital and 2 2p orbitals combined to make 3 sp2 orbitals. What do we have left over? Somebody say it. So we have 2 2p's. How many 2p's do we have total? 3, right? So we have 3 2p's total. So when you do this sp2 arrangement, you have an extra 2p orbital, right? You have an extra 2p orbital. And so that's going to be an empty orbital that you can put stuff in, right? Here's an example. We're going to show, this is the end product is BH3, borane, boron hydride, or it's called borane, B-O-R-A-N-E. So you have boron with the 2s and 2 2p orbitals hybridized to make these sp2 hybrid orbitals. So you have 3 sp2 orbitals, sp2, 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 right? And they have kind of like a, let's talk about the lobes in a second, but when they combine with H's, now you have BH3, right? With the 3 sp2 orbitals, right? These back lobes are kind of in the back of the molecule, back of the orbital, right? So okay, so this is a bonding orbital, right? See it? Bonding. That's a orbital for a bond. What do you think is in the back unoccupied orbital? It's bonding. This is
Antibonding?
antibonding, yes. So what would happen if some pair of electrons or something would come in and attack this antibonding orbital? It would break this bond, right? An antibond, right? So that's kind of one of the uses of antibonding orbitals. They're empty orbitals that can be occupied and that breaks the original bond.
What is the inner functioning of the hybridization? Why does it go from what we see on the left to that trigonal planar shape?
Yeah, well, so what we're doing is this is sort of a theoretical explanation for it, because we're starting with thinking about atomic orbitals, right? 2s, and you have the two 2p's that we're using, right?
Yeah.
And so this is kind of like a theoretical explanation, and this is actually what really happens. So what we're trying to do is step from what you already know to what you are learning, I guess. It's not like this is actually hanging around and then it's like, oh, I'm going to hybridize, right? It's like, but what we're doing is we're combining the concept that you know, 2s and 2p's, into what the real structure is of this molecule. And also, of course, the 3 H's, it's not like they just kind of attach in there. I mean, this is like we're doing a sort of a stepwise explanation for how it's, you know, how the orbitals are arranged. But it's not like this happens like physically, like A, B, C. It's like, this is actually kind of, this exists already in this structure, right? Hopefully that helps. But what's remaining? There's a 1s and 2 2p's. So there's a free 2p orbital. We haven't, just 3 of them, right? Where's that? Can't see it, right? It's actually coming towards you and away from you. It's actually kind of in front of us. It's in front of us and away from us. So it is there. And is there anything inside? There's nothing inside. It's an empty orbital. Actually, it's an unoccupied p orbital, right? It's an empty p orbital, okay? And does that mean that nothing can go inside? No, it can't. The things can go inside. That's actually, that explains the reactivity of this molecule. There's a lot of times, we'll call this a Lewis acid shortly. Like this is a Lewis acid because it has a space for electrons to come in, and you just can't see it very well. But there's an orbital, an empty orbital that's coming towards you and going away from you. We'll see that visually shortly. But no, it's there. It's there, of course. You have 2 2p's, but there's 3 total, right? 1 p orbital is left unoccupied. It's not clearly shown, right? It's there. Okay, what about SP? SP, well, okay, you have 1s and 1p. What's left over? There must be 2 p orbitals left over, and there will be the same kind of thing left unoccupied. So now the 1s and the 1 2p orbitals combine to make 2 sp orbitals. An example is beryllium hydride. Beryllium hydride. So we have a 2s and 1 2p orbital combine and hybridize, and now you have an sp on one side, sp on the other. What's the geometry? Let's go back to the last slide. Somebody mentioned this is trigonal, right? It's a trigonal planar thing. This is like a planar molecule. It's not like it's bent or not like tetrahedral like sp3 was, right? This is trigonal planar. Back to sp, this is linear. It's a linear arrangement of 2 sp orbitals, right? Okay, and then with 2 hydrogens, they bind and it's a linear arrangement. Where are the unoccupied 2 p orbitals? They're
to that.
One's going up and down.
Yeah.
The other's coming towards us and away from us, right? So they're there. They're there. They always have to be there. If you're an sp2 or sp, you have unoccupied p orbitals. Okay, and this just shows, this is a kind of electron diagram that shows unhybridized 2 electrons on the beryllium. And when you hybridize, now you have 2 sp orbitals and 1 electron each on the beryllium. Of course, if you add the hydrogen, then you have an extra electron each. But there's also these 2 p orbitals that are unoccupied. They are unoccupied, okay? They can become occupied, but right now they're unoccupied. ammonia and water are semi-tetrahedral. And sometimes, and this brings up a good point, that not all hybrid orbitals participate in bonding. The ones we just showed were, but sometimes lone pairs, sometimes the orbitals contain a lone pair of electrons. Here's a great example. This is ammonia, right? NH3. So the overall shape of this is what? It looks like it's tetrahedral, right? Yeah, it's totally tetrahedral. And it's kind of like we have four things on it. We have a H, 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 and a lone pair, right? And with those four things, it adopts an sp3 hybridization. So you have four sp3 orbitals, so it's tetrahedral, sp3, 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 and sp3. And they all, and what's the shape? It's tetrahedral, right? Everything wants to be apart from each other because of repulsion, right? But then water looks kind of similar. It's weird though. There's a little weirdness about water. I mean, it looks very similar, right? Water looks tetrahedral, and it's roughly tetrahedral, right? Roughly, I think it's tetrahedral is 109.5, so it's pretty close, semi-tetrahedral, right? You would think that these are also sp3, 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 and sp3, right? For hybridized orbitals. It's something weird going on where ammonia is definitely sp3, but water is not. It's just something about the energy levels of the orbitals makes water, it's actually unhybridized. It does, the structure of water is weird. It'd be convenient if everything was nice and consistent, but something that's a little odd with water due to the energetics of the orbitals. So the bonding angles of ammonia are 107.3, and in water they're 104.5, both close to tetrahedral. But energetically, water is strange. The 2s and the 2p orbitals have a large energy difference, preventing it from hybridizing. So there's actually, water appears to be unhybridized. And there is a homework problem. You can take a look at it if you want to study this a little more. It's an interesting phenomenon. Yeah. Okay. It looks hybridized, but it really is not. Okay. In most cases, most molecules where we have lone pairs, they occupy hybridized orbitals. That's a general rule. Okay. Usually, like with nitrogen and molecules, and you have a lone pair. It's usually going to be a hybridized sp3 thing. Keep that in the back of your mind because we're going to see that again soon. Okay. That in most molecules, lone pairs occupy hybridized orbitals. Okay, now back to organic chemistry. Double and triple bonds of organic molecules, they usually would utilize sp2 and sp orbitals. So single bonds. So in a multiply bound molecule, like with the double bond, you have two bonds, right? There's a single bond, which is going to be an sp2 or sp hybridized orbital. We'll see that in a second. Then you have the double or triple bond, and those are using the extra p orbital, which is unhybridized. Okay. Example. This is ethene. Ethene is a C double bond C. So this is a doubly bound molecule, right? It's C double bond C. And this doubly bound molecules are sp2 hybridized on carbon. So the carbon is sp2 hybridized. And just looking at the left carbon, we have three single bonds, right? You have a carbon to the H, carbon to the other H, carbon to the carbon. Those are all in the sp2 hybridized orbitals, sp2 hybridized orbitals, okay? And then you got the second bond, and that's the one that's kind of going up and down, right? And that is in the p orbital system. This is sp2, using sp2 hybridized orbitals. And the one that's the second bond, it's just two bonds total, right, is using the p orbital. Now this should say sigma and pi. It's just a PowerPoint error. But usually we call the first bond the sigma bond. It's a sigma bond, right? The second bond is the pi bond, okay? So in a double bound system, it's sigma bond, pi bond, okay? What about a triple bond? Triple bond is going to use the sp arrangement, sp hybridized arrangement. So this looks crazy. You know, when I learned organic chemistry, we had to draw this on our exams and stuff. I'm not making you draw this, mostly because it's really hard for me to grade this. So don't worry about the drawing of this. You can, you know, for practice, you can try drawing this, but it's a little crazy. I usually on a whiteboard in class, I'll draw this just for fun. But this is ethyne, which is a C triple bond C. There's 3 bonds, bond, 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 right? 3 bonds between the 2 carbons. The first bond is a sigma bond, and that is using the sp hybridized orbitals. And then there's also a sigma bond, I mean, the bond to the H, so the CH on the back here, that's also sp. So it's like sp, sp, right? And then where are the other 2 bonds? Those are in the pi bonds, and those are using the extra p orbitals. Because you have to remember, if it's sp, this is sp. This whole thing is sp, right? You have 3 p orbitals. 1 is in the sp hybridized orbital. You have 2 additional p orbitals. One is kind of going up and down, right? Up and down. That's your second bond, is up and down, right? And then you have the other p orbital, which is going back and forth, back and forth, back and forth, back and forth, right? So this looks pretty crazy. It's not that hard to understand, though, right? 3 bonds. You have the sp bond, and then you have the 2 additional bonds, which are in the they are occupied p orbitals, the unhybridized p orbitals. Okay, cool. All right, so how do we determine chemical structure, like actually in the laboratory? And this is, you learn more about this in organic too. Also, how do we establish a structure and, you know, figure out the chemical structure? One of the things we can do is figure out the empirical formula, which is like what elements are present in what ratios. Like, is it C6H6 or C6H5Br? In the it's like the number of elements, what the, you know, and those can be determined by a technique called elemental analysis, which analyzes the elements. And then, or we can use something called mass spectrometry. And both of these are things, you know, you can do in the lab. We actually have a couple of mass spectrometers on campus. I have one personally that I maintain myself, a mass spectrometer. And so you know, one tells you kind of what the elements are. The other tells you what the molecular weight is. Like, is it 108.5, or, you know, something like the molecular weight, the sum of all the atomic masses, right? That's what mass spectrometry tells you. Elemental analysis will actually tell you, you know, how many carbons, how many hydrogens, how many BRs, how many oxygens and nitrogens. That's what elemental analysis tells you. Okay, so these are experimental techniques we can actually use in the lab. If substances have the same empirical formula but a different connectivity, and somebody asked this earlier, last lecture or the lecture before, these are called constitutional or structural isomers. So look at these 2 molecules. They both are C3H7Cl, right? They're both that. But are they the same molecule? No. One case, the chlorine's in the middle. The other case, the chlorine's on the right. So these are different molecules, but by the molecular weight or molecular formula, empirical formula, they would look the same, right? But the structure is different, right? So that's going to be called a constitutional isomer, and you're going to be seeing constitutional isomers like crazy in some of the upcoming chapters. So that's what a constitutional isomer is. To fully characterize the chemical structure of a molecule, and like looking at these are chemical structures, right? To fully characterize the chemical structure, we need to use something called spectroscopy. And we will actually learn this in Organic 2. It's the first chapter we learn in Organic 2, NMR spectroscopy. This is an example of an NMR spectrum. These weird peaks correspond to, in this case, is ethanol. This is CH3CH2OH. And so you're going to learn this in Organic 2. And this actually tells you the chemical structure, not just the formula, but the structure of the molecule. It's pretty amazing. I love NMR. It's really cool. Okay, and then there's a couple ways to represent 3D structures of molecules. Ball and stick, these are a couple of different ways to represent structures, and computers do this really well. And this is ethanol versus dimethyl ether. These are two different organic molecules. But ball and stick is kind of like, you see the little balls or the atoms, and sticks are the bonds. So this is ethanol, CH3, CH2OH. This is dimethyl ether, which is CH3, oxygen, CH3. These are actually, these happen to be isomers also. Totally different molecules. Ethanol boils at 80 degrees. Dimethyl ether boils at -23 degrees Celsius. So it's basically a gas at room temp, right? And there's also something called a space filling model, which is this kind of weird computer generated image here. And these are both C2H6O, and but they are constitutional isomers, right? Okay, this is a quick worksheet we'll do. I'm going to jump this onto my second webcam. So you should be doing this. Can you hear me? Can you hear me? You all hear me, yeah?
Yes.
Okay, good. Hello, hello. Okay, do you see my big sheet of paper? Somebody say yes?
Yeah.
Okay, cool. All right, so Kekule structure. That's a Kekule structure, right? And this is you know, we're drawing all of the bonds, right? Each of the bonds. And 1 second. Yeah, okay. And right, what is, looking at these other ones as for guidance, what does condensed mean? Condensed, like in this second case, is like we say CH3, CH2, CHBr, CH3. That's the condensed formula. How would a condensed formula look for this top molecule? Anybody want to say it? It's because we're condensing and not showing all the lines, and we're just drawing the chemical structure, but in a condensed format. So maybe it's like CH3, CH2, CH2OH, right? Now this is my own style, but I like to write H3C for the left one like this, because the C is going to be bound to the second C. So you could either say H3C or CH3. I like to say H3C. It was H3C, CH2, CH2OH, right? That's a condensed format of this propanol molecule. And you could also, like I said, you could just as well say CH3, CH2, CH2OH. So that's also fine. CH3, CH2, CH2OH. My preference is the top, but your choice on this one. That won't make a big deal. Okay, skeletal. So skeletal kind of looks like Kekule, but we usually don't draw each of the carbons. And I like to, for skeletal, I like to say zigzag. It's a zigzag. How many carbons are in this molecule? 1, 2, 3, right? So to draw the skeletal format, I like to draw a 3-carbon zigzag. Okay? 3-carbon zigzag, right? And those are 3 carbons, right?
Is that a butane?
That's not butane, it's propane.
No, propane.
Propane, you got it, yeah, propane. So propane's 3 carbons. So it's propane so far, but where is a hydroxy group, the OH? It's maybe on the right side carbon. So now I would draw the OH like this. And there we go. That is the skeletal structure of this. Most Gen Chem students really freak out. When you start drawing these, they're like, oh, I cannot understand this. You know, what's the meaning of this? But you're going to get better at this. You're going to understand this really quickly. Of course, that's a CH3, that's a CH2, and that's a CH2, right? CH3, CH2, CH2, okay? All right, so how do we, now let's look at this next one, condensed. Condensed, how many carbons are there? 1, 2, 3, 4 carbons, right? 1, 2, 3, 4 carbons. Maybe I'll start with the skeletal. So what should I draw first? Anybody want to say?
CH3.
How many carbon zigzags should it be? 1, 2, 3, 4. It's a 4 carbon zigzag, yeah?
butane.
So 1, 2, 3, and there's 4. 4 carbons, right? 1, 2, 3, 4, yeah?
Yeah.
Where is the Br? Is it on carbon 1, carbon 2, carbon 3, or carbon 4?
Carbon 3.
3.
It has to be carbon 3 because that's where the CH is there, yeah? So yeah, it'd have to be a 3rd carbon. So I just go Br. There we go, that's a skeletal structure, right? Now, what about the Kekule? Well, the Kekule is gonna kind of look like this other Kekule, but how many carbons total? It's 4, so use the top as a model. We're gonna say C, 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 and maybe fill in some H's, H, 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 Br, H, 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 right? So that would be a Kekule structure of this molecule, all right? Which one should you get the most used to drawing? The skeletal. We're gonna be drawing skeletal exclusively very shortly. So you gotta get kind of comfortable with, understanding the meaning of skeletal. And this problem kind of helps us with that. What about this bottom one? No, second to bottom, this one. Okay, how do we draw the condensed of this? What should I start with? It's maybe a H3C. This C double bond O, how should I draw that? Just condensed, it looks like it's CO, right? Okay, and then CH, and then what else?
CH2.
CH2. Is that a very illustrative way of drawing the molecule? No, this is much better. But what I really want you to do is kind of get down to the skeletal structures, right? How do you draw the skeletal? How many carbons? Always start with the carbons. We have 1, 2, 3, 4. There's 4 carbons, right? So what do you start with? Maybe a 4 carbon zigzag. So point, 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 4 carbons, right? Where's the C double bond O? On carbon 1 or maybe 2?
It's 2.
2. Look at that. There's your C double bond O. And then for the double bond, the C double bond C, I just draw this guy like that. And in skeletal, you typically do not draw H's. However, if you have an OH or an H2, you might draw the H's for those. But there's no OH's here. Yeah. Okay, this is scary. Now we're given the skeletal of this triple bond thing. Maybe it's the easiest to draw the Kekule first. I think it's easy to go from skeletal to Kekule, right? How many carbons?
1, 2. 2?
3. 1, 2, 3, right? 1, 2, 3. So maybe draw C, C, C. Start with that. 3 carbons, right?
Yes.
Carbon, carbon, carbon. How many H's are on the left side one?
3. 1. 1.
It has to be 1 because there's 3 bonds already on the carbon. So 4 minus 3 is 1. And so there's a single H. And of course, now you got the triple bond. Yeah, we're cool so far, yeah. How many H's are on the, we'll call it carbon 3?
2.
Done.
2.
Oh,
2.
Yeah.
I have a question.
And then you have OH. Yeah, question.
Where do you see the 3rd carbon?
So when I'm looking at this, I'm calling that carbon number 1. I'm calling that carbon number 2. I'm calling that carbon number 3. So that's a carbon, carbon, carbon.
Okay.
So when it's like cut halfway like that in the line, we can assume that there's another carbon.
Yes, yes, absolutely. And this is, we're going to call this thing later, we're going to call it an alkyne. I'll use that name later, alkyne. Whenever you have an alkyne like this, which is a triple bond, you always kind of explicitly show, like, you know, you assume carbon, carbon, then there's like another carbon off of it. And we never will draw this like this. Like never. Don't do that. You're because that's also, I mean, the geometry of an SP, which the triple bonds are SP, right? The geometry is SP and SP, and those are linear, right? So I'll just draw this HN for fun. I don't have to, but yeah, it's a linear relationship between like this CH versus the C triple bond C, right? So this is 180. This thing is 180 degrees from like that carbon, right? It's 180 degrees. It's linear, SP, right? Okay. Let's do the condensed.
I have a question. So how come when it's a double bond, we draw another line?
Draw what?
Yeah, how come like when it was double bonded up there?
Yeah.
We drew another carbon.
The angle. Well, so the thing is, double bonds are angled. So it's just like if I'm just start drawing like the H's here, there's an H here, and there's an H here, and an H there. You know, the carbons are sp2, right? For a double bond, it's sp2. Triple bond, it's sp. In this case, I mean, this is 4 atoms. 1, 2, 3, 4. In this case, it's 3 atoms. 1, 2, 3, right? So we just draw these a little differently. With the double bonds and the triple bonds, we draw them a little differently, I guess. Let's draw the condensed of this guy. And the condensed is really not something that's very useful, but we're just for the sake of learning it, we maybe it's to learn why it's bad when we learn it. And you know, some molecules you'll see in, you know, in your classes will be in condensed format. Well, all we're going to do is say HC, and then C, HC, C, CH2, OH. And again, that's not a very useful way to draw the molecule. I would say Kukule and skeletal are better, and skeletal is actually the best and the simplest, in terms, the most efficient way to draw organic molecules. Okay, cool. All right, back to the PowerPoint. We just did these guys. Now we're basically at the end of the chapter. These are a couple of cool problems for you to try. I'm not going to go over them. Carvone is a substance responsible for the odor of spearmint, very intense spearmint smell. This is a structure. Tell how many hydrogens are bound to each carbon and give the molecular formula. Okay. Real quickly, I'm just going to kind of, you know, step through this molecule and say, you know, how many hydrogens. You should know this. I mean, if you're struggling with it, you need to come to office hours. CH3, this is an alkene, or a double bond, and there's a CH and a CH. So there's a CH, that's a CH2 actually. Remember, the way you do this is 4 minus number of bonds, right? 4 minus 1 is 3, it's a CH3. 4 minus 2 is 2, so this is CH2. So CH3, CH2, CH, CH, CH3, of course, no H's there because the carbon has 4 things on it, CH2 and CH2. So if you add all that up, you'll get a molecular formula. And then you can check yourself on Wikipedia or something. Wikipedia will tell you the chemical formula of this.
Is that called the benzene ring?
This thing is, this one is not. The bottom one will be. Benzene, when I said benzene, a benzene is a 6-member ring with 3 double bonds. And there's 2 here. So this is not a benzene.
So in the real world, will the molecule actually bond back on itself like that in the way that it's drawn in this
top one?
Yeah.
You know, it's the 3-dimensional structure is going to look a little different than this, but yeah, it's mostly, you know, you got a 6-member ring and you have the C double bond O. You have a bunch of H's. So you could probably, if you Google like three-dimensional structure of carbon, you can actually get a model, a computer model that you can rotate on your computer. But yes, it basically looks like this. Yeah, 6-member ring, and you got a couple things on it. Yeah.
Quedaron papas, no sé qué, ¿para qué grababan todo?
Louder. Hello? Can't hear you. Okay. So these are more examples. Adrenaline or epinephrine. This is a benzene. When we see this kind of thing, that's what a benzene looks like. Same kind of thing. So find all the H's and make a formula, and then see if it matches like Wikipedia. Estrone is a steroid hormone. How many carbons? Okay, I see 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. How many H's there? 1 is a CH, 2, 3. And then any H's here at these positions? No H's here. Because that would be more than 4 bonds to carbon, right? So it's like CH, 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 CH2, CH2, CH, CH, CH2, CH2, CH3, CH, CH2, CH2. So if you add all that up, and you can get the molecular formula. That is that could be a quiz problem. And the quizzes are slowly creeping up on us. I'll tell you when we're gonna have quizzes, but we're slowly getting to that point where we're gonna do quizzes. All right. Cool. Check your answers using Wikipedia. Good practice. Good practice. Do these problems, right? As well as the homework if you're able to do the homework. These are a couple more. Converting skeletal structure to Kakule. So it's a little bit of work. I mean, you have to draw all the CHs for all of these. And then you can determine the molecular formula. So this is Vioxx, it's a painkiller. Viagra, OxyContin, cholesterol, benzylpenicillin. This is really good practice. See, if you cannot do this at all, you're probably behind in the course of it. So give this a shot, and if you're stuck on these, come to office hours, right? Okay. Wikipedia, and then this is one where we're just determining hybridization. Also a potential quiz problem we're going to see. sp3, sp2, sp. So, are there any SPs anywhere? Let's think about SPs anywhere. Any SPs on the left? Yes or no?
No.
No, there's not. SP are usually triple bonds, right?
Yes.
The only SP I see anywhere are these 2 carbons.
Yeah.
Those are SP, right? Okay, sp2, well, there's a lot of sp2s. sp2s are going to be double bonds, like that's an sp2, that's an sp2, that's an sp2, 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 sp2. The benzene CHs, all the benzene carbons are sp2. sp2, sp2, sp2. These are all double bound, right? Okay, what are sp3? Well, there's tons of sp3 also, like the ch3, sp3, right? That's a ch3. The dash, dash, dash means it's going away. The wedge means it's coming towards you, right? So yeah, sp3, 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 sp3. I'm not gonna go through all of them. What about like an oxygen? Look at this. Think about this oxygen. There's 2 lone pairs on there. We're not drawing them, but there's a lone pair. There's 2 lone pairs, right? What do we say it is? If it's got lone pairs on it, it's typically sp. sp3. sp3. So this is sp3 because it's got 4 things on it. It's got a bond to carbon, another bond to a carbon, lone pair number 1, and lone pair number 2. I'm just not drawing the lone pairs, but yeah, you have 2 lone pairs, right? What about this OH up top? It's also 4 things are on it. It's a bond to carbon, a bond to H, lone pair number 1 and lone pair number 2 that we're just not drawing. And for you guys, I'd recommend drawing the lone pairs in, just to remind you that that they're there. Nitrogen. So oxygen and nitrogen in normal organic molecules, singly bound to things are going to be sp3. So this nitrogen is bound to 4 things: a carbon, another carbon, another carbon, and a lone pair. So is SP?
SP3.
SP3, yeah, exactly. You're getting it, right?
Oh, can we assume all the oxygens on the right, they all have lone pairs on them too?
Yeah, yep.
Okay.
Now, but however, like this one has how many lone pairs? 2, right? But these actually have 2 lone pairs also. So this has 2 lone pair, and lone pair. But this is a doubly bound oxygen. So it's not sp3, it's sp2.
2.
So the doubly bound oxygens are sp2, just like the doubly bound carbons are sp2, right? Okay, that's it for this chapter. Now chapter 2. All right. All right, so we're getting more into structure and reactivity of molecules. A little bit of theory, kinetics and thermodynamics, which are kind of sort of gen chem-ish. Then we're getting into acids and bases, nucleophiles and electrophiles. This is more organic-y and more testable or quizzable. And then functional groups, that's a huge organic topic. That, yeah, that'll be fun. All the different kinds of alkanes, which are usually those sp3 hybridized carbons, CH3, CH2, stuff like that. Straight chain, branch, cyclic. Naming, we're gonna get into naming. Naming alkanes, there's a whole strategy and protocol to use for naming and nomenclature. And then the structural and physical properties of alkanes. And then we're gonna end with rotation of single bonds and ethane and propane and butane. That's gonna be another fun thing, okay? We are a little behind schedule. It's not a big deal. We usually get a little bit behind, and we also have a couple of these buffer days in the course, so I wouldn't worry about that. So if you look at the syllabus, you know, yes, we are behind, but that's not a big deal. Don't worry about that. I'll keep track of the schedule. All right. So firstly, kinetics and thermodynamics, basic theory of chemical reactions. How do we know what products to expect from a given reaction? So there's kind of 2 things to consider: chemical thermodynamics and chemical kinetics. Thermodynamics determines the extent that a reaction will go to completion. How far does the reaction proceed from like molecule A to molecule B, right? That's thermodynamics. Chemical kinetics is concerned with the speed that a reaction goes. So just because a reaction is favored thermodynamically doesn't mean it'll actually occur unless kinetics are favored. So kinetics is concerned with the speed that a chemical reaction goes to completion. How fast does the reaction proceed? So then there's ways to control reactions. Under thermodynamic control, the most stable product is formed. Under kinetic control, the fastest formed product is favored, okay? So we'll see those concepts too. So equilibria are governed by thermodynamics of chemical change. When concentrations of reactants and products no longer change, so if a molecule's, you know, we have A and B and they're going back and forth, once they're no longer changing, the system is said to be at equilibrium. So this does not mean that no reactions are occurring. It just means that, like in like this example, A and B, it just means that A isn't changing and B isn't changing. The amount of A's is the same and the amount of B's is the same. And we show this with the equilibrium constant. K equals products over reactants, B and A, right? And if we have A plus B going to C plus D, it's still products over reactants. C times D divided by A divided by B, okay? A large K value means gone to completion, or we'll say product favored. So a big K value means we have a lot of B or a lot of C and D, okay? Then there's this thing called Gibbs free energy, which is it's a thermodynamic property that relates a value called delta G to R, gas constant, temperature, and the natural logarithm of the equilibrium constant. So delta G is related to the equilibrium constant. When an equilibrium constant is big, so a product favored equilibria, then delta G is small, right? So you should know that from Gen Chem. Really tiny delta G means the reactions went product favored. When K is less than 1, then delta G is greater than 0 and reactants are favored. This just shows a couple examples of kind of like K values and, you know, like B and A. So B is the product and A is the starting material. So B, so it's a little backwards, I guess you'd say. So when K is really small, when K is really small, really tiny K, you have tons of starting material, tons of left material, right? And of course, delta G, and these are just 2 units, kilocalories and kilojoules. Usually in this course, we deal with kilocalories, okay? So when we have tons of the left material, then the delta G is a big number, right? A positive number. And then the opposite situation, when K is a huge number, K, it's like very product favored. So we have lots of B, 99.99% of B. So it's like, we'll say a complete reaction. The reaction went from A to mostly B. Then delta G is very small, right? So the big thing though is that it's logarithmic. And so a big difference in like A and B is kind of a small difference in the delta G, and that's due to the logarithmic function. So small difference in delta G gives large difference in K. Okay, this is because we have a natural logarithm in there. All right. So delta G is related to changes in enthalpy and entropy. So these are 2 thermodynamic principles also. Enthalpy is a measure of the energy in the system, which is basically bond strength, right? Some bonds are nice bonds and happy bonds. Some bonds are kind of weak bonds or not very not strong bonds. They're strong bonds, right? And strong bonds and kind of weak bonds, right? And if you're forming a whole bunch of strong bonds, it's kind of favored with enthalpy. Entropy is a measure of disorder. So they're actually kind of different. Top is the more the bond strengths, the bottom is the measure of disorder, okay? So delta G is negative, or is delta H minus T delta S. So the change in enthalpy can be estimated very easily, and we'll do this in this class. When we see some real chemical reactions, we're going to calculate it. We're going to actually calculate delta H. Not there yet, but we will. It's delta H is the sum of the strengths of bonds broken minus the sum of the strengths of the bonds formed in a chemical reaction. So you add up everything that's broken, subtract everything that's formed, and that gives you delta H. It's actually pretty easy to do. All you need to know are the bond strengths. And we have little tables of that. So this is actually an easy thing. Okay, so when delta H is negative, it's favored, a reaction is favored. And as if the products are more stable in the reactants, which often happens when when A goes to B, if the products are more stable, then delta H is negative. Okay, we call that exothermic. When delta H is positive, that's disfavored, and that's when the product is less stable. Okay, so delta H and delta G will relate. Usually the entropy, the delta S, is not even important at all. In that case, you just say delta G is basically semi-equivalent to delta H. Very often, the entropy just disappears. It's not even, it's zero. It's often a zero value. Okay, delta S measures the change in order in the system. For many organic reactions, it's zero. If A goes to B, it's zero. When do we actually see a positive entropy? When like A goes to B plus C, like if I have molecule A that breaks apart to make molecule B and C, then yeah, that's actually there's a lot of disorder there, right? You're increasing the disorder of the system because one molecule getting converted to 2 molecules actually increases disorder. But most of the time we don't do this. Most of the time A goes to B or A plus B goes to C plus D, in which case there's no entropy. So the T delta S falls out. We don't even see it, okay? All right, so for many organic reactions, entropic term is 0. But entropy increases if there are more product molecules than reactant molecules. That's a very simple summary of entropy, okay? Delta H will be really easy too, because we can just calculate it. We will calculate it, probably next chapter. So rates of reactions. That was a little bit of thermodynamics. There's a little bit on kinetics. And kinetics is a pretty complicated thing. We're just going to review a couple principles for kinetics for now. in contrast to the stability of the reactants and products, the rate depends on three things. The rate of the reaction depends on three things. The activation energy, which is going to be kind of like the little energy barrier you have to overcome for the molecule, for the reaction to occur. The concentration of one or more reactants, and temperature. Those three things will define the rate of the reaction, or the kinetics. So potential of energy system changes with time through an intermediate structure called a transition state. You should have learned a little bit about this in Gen Chem 2. So like if I have methane plus oxygen, right? And those can combust to make CO2 and water. Well, it doesn't happen spontaneously. There's actually an energy barrier, transition state. And it's actually a pretty large transition state. Because if I have methane and oxygen in a flask, they don't just combust, right? You need a spark. You need a little match, a spark of energy to actually get it combusting, right? Right. So yeah, so there's a transition state for every chemical reaction, and it's an energy barrier you have to overcome for the reaction to occur. It's called EA. And this is a nice summary of the idea of kinetics and thermodynamics. Kinetics kind of refers to the top part of this graph and the energy. And the thermodynamics is kind of the bottom half of like the relative stability of starting materials and products, right? That kinetics is the top, thermodynamics is the bottom. And this is an exothermic reaction, but you need to overcome the transition state to actually, for the reaction to occur. Even if the reaction is favorable thermodynamically, it may not proceed. Methane does not spontaneously combust, nor do we. Even though our spontaneous combustion would be thermodynamically favorable, fortunately for us, we have a lot of energy barriers that prevent us from combusting. The higher the activation energy, the slower the reaction, okay? So the concentration of reactants affects the rates via something called a rate law. If we consider A plus B going to C, there's kind of two ways we can see this reaction. One is a first order reaction where the rate of the reaction depends on a rate constant, it's called K, times the concentration of A. So the rate of the reaction would depend on A, right? So if you have lots of A, the reaction goes fast, okay? There's also something called a second order reaction where the rate depends on A and B, right? And usually when you have these two situations, the first order case and the second order case, in the first order case, one molecule is present in the transition state. Usually A would be involved in the transition state. In the second order reaction, both starting material molecules, SM is starting material, both molecules are involved in the transition state, okay? So the rate constant and the rate law are determined experimentally. It's not something we can easily just calculate, like enthalpy, for example. The nature of the rate laws does give us vital information about how the reaction occurs, something we call the mechanism, all right? There is this scary equation, and you're not gonna have to do anything with this equation in this course. It's called the Arrhenius equation. But what it basically does is it relates the rate constant to the energy of activation, which is just an energy barrier, right? And T, which is temperature. And so, so this equation occurs. A is the maximal rate of the reaction, the fastest the reaction can possibly go, okay? And so K is a rate constant. It's not the same as the equilibrium constant. These are totally different. This is a rate constant, this is the equilibrium constant, right? A is a constant, the maximum possible rate for a given reaction. R is a gas constant, it's just a constant. EA is activation energy, which is an experimental quantity. So just as one way to just think about this equation is that as temperature increases, you'd think when temperature increases, things go faster, right? Reactions go faster, and that's what happens. As temperature increases, the EA divided by RT term gets smaller because T gets larger, right? And then this approaches zero because E to a very, very large, E to a as temperature gets higher, this E term approaches, the exponent term approaches 1, okay? And ultimately then K, the rate constant, approaches A. So as the temperature gets higher and higher and higher, in the chemical reaction, temperature gets higher, 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 the rate constant approaches the maximal possible rate. So that just kind of shows, that explains that, you know, you increase temperature, reactions go faster. That's what it shows. This is, you can actually study this quantitatively. All right. In general, if I increase the temperature by 10 degrees Celsius, it'll increase the rate constant by 2 to 3. So that makes sense. And we see this in organic chemistry, that you cook things and they go faster. Cook a chemical reaction, apply some heat to it, and it goes faster, okay? 10 degrees Celsius, about a rate of 2 to 3. So that's pretty much what, you know, and you don't need to memorize that, or really, you're not going to ever use this equation in this course, but it just kind of explains the relationship of temperature to reaction rate. Okay, I'll start this and then we'll stop. Okay, so I want to just mention acids and bases, and then we'll get into it next time. Bronsted-Lowry acid-base theory. An acid is a proton donor. We donate a proton, H+. Bronsted base is a proton acceptor. So it's the conjugate base, usually. Water can be a base or an acid. We're going to show it be a base initially. So this is actually a chemical reaction, and you have not really seen any chemical reactions yet in this course. In chemical reactions, we will draw the mechanism of the electron movement with arrows, kind of the way you did with resonance, right? So water can grab a proton from an acid. Like I did in resonance, I would actually recommend circling the lone pair. So I would circle the lone pair, and there's 2 arrows. Arrow for the lone pair to grab the proton, and then the bond breaks and pushes electrons onto chloride. So this is actually a chemical reaction we're showing. Your first chemical reaction of this course. And then that makes hydronium ion and Cl-. Okay? So this is water acting as a base. Water can be a base or an acid. I'll stop shortly, slide or 2. Here's a case where water is an acid. So it's giving up its proton. So ammonia, and there should be a lone pair on NH3, and you should circle it too. So NH3 ... circle. Imagine circling a lone pair right there. Can grab a proton from water and push electrons onto oxygen. So there's some lone pairs that are kind of hard to see, but they're there. And that makes ammonium ion and hydroxide ion. So this is a case where water can be an acid or a base. Okay, we will do the last slide. All right. So this just shows review of Bronsted-Lowry acid-base theory. So water is in equilibrium. Water is in equilibrium with 2 waters, or in equilibrium with H3O+ and OH-. Okay, this is Gen Chem stuff. We define Kw as the concentration of H3O times the concentration of OH-, and that's 1.0 times 10 to the -14th. And this is in a normal neutral water, and when we determine, of course, H+ and OH- are going to be equal, and that defines the amount of H3O+, which is 10 to the -7, and that's the 10 to the -7 times 10 to the -7 would be 10 to the -14. pH of water then is the -log10 of that, of the amount of acid. Of course, we know that water, neutral water, is pH 7, right? But if you have acidic water with more H+, pH is less than 7. And if you have basic water, pH is greater than 7, right? So very cool. We'll move forward from here. We're getting to some really cool stuff, and I'll just stop the lecture now. And I'll hang out for a couple of office hours type questions, but I'm going to stop the recording now. Stop.